Hello everyone. This video is going to be about, it's for the revision of the year 12 final exam and for the mechanics unit. And yeah, it's going to be everything about mechanics we've covered so far this year. So feel free to ask any questions in the comments. So basically, in this year, we have learned 1D, 2D kinematics, motion of objects, forces, which includes three laws of Newton's three laws, conservation of energy, work energy theorem, conservation of momentum, which includes collisions, explosions, and rocket problems. We also have circular motion, which is a separate topic from the usual mechanics stuff, but I'm still going to include it. And finally, for HL students, we have learned the concept of gravitation and fields. So in this video, I'm just going to talk about 1D, 2D kinematics very quickly because there's nothing really interesting going on in IB physics for kinematics. So just going to cover it really quickly and cover some basic definitions and equations and stuff, and go through some problem-solving strategies. So the first thing for 1D kinematics is that you have to know what vectors are. And I'm just going to explain it briefly now because we don't need to know, we don't need to do any computations of vector quantities. Basically, vectors are quantities that have a direction, not just scalars. Scalars are quantities that only have a magnitude, they don't have a direction. And one such example is time. Time does not have a direction. For vectors, there are some examples such as displacement, velocity, and acceleration. And displacement is a vector because we're talking about the direction of the distance from one point to another point. Not the direction, to be exact. It's a quantity that has a direction. And distance and speed are scalar quantities. Displacement and velocity are not. So be mindful of that. We also talked about Suvat equations, and Suvat equations are only applied, this is quite important, only applied when you have a uniform acceleration. The derivation of Suvat equations are quite intuitive from the area and the slope of ST-VT-AT graph. And yeah, I'm just gonna cover the ST-VT-AT graph first. So basically, you have an ST-VT-AT graph here. And if we have, so this is 0, so if we draw a line like this, the area means nothing. You don't need to worry about the area. The slope means the velocity. The definition of velocity is basically the change. Average velocity is basically the change in the total displacement over the change in time. The instantaneous velocity means when at that instant what the velocity is. And if we look at it in a graphical sense, it means the slope of the tangent line when you draw. So for example, if you have like a curve that's like this, then you want to find the instantaneous velocity at this point. So you draw like a tangent line and you find the slope of that tangent line. And the slope of that tangent line means the instantaneous velocity. So this is going to involve some calculus, but I'm not going to cover any calculus in this video. So just be reminded that it's the slope at that point. I'm still going to write out the equation, but it's not necessary to memorize this. this is the ST graph. For the VT graph, it's going to be a little bit more different. So if we have a velocity line that's like this, then the area underneath the curve means the total displacement. The slope means the acceleration. And same thing, average acceleration is basically the total change in velocity over total change in time. Instantaneous acceleration, we definitely won't cover this in IB physics because we rarely talk about in pure kinematics, we rarely talk about situations where acceleration actually changes. But instantaneous acceleration is the same concept as instantaneous velocity. It's basically the derivative of the velocity and the slope at that point. So that's the way you interpret ST-VT graph. And finally, we have the AT graph. So the AT graph is the same concept. We have, like, for example, let's say a horizontal line. Then the area underneath is the velocity. So the area is the velocity. And the slope is the change in acceleration. Change in acceleration. Yep. So that's it for ST, VT, AT graph. We rarely talk about the slope on an AT graph in IB physics because we always use constant acceleration. So you'll always see an AT, not always, but you usually see an AT graph that has like a horizontal line. So yeah, that's it for ST, VT, AT graph. And when we're talking about Suvat equations, all of these equations are actually derived from these areas and slopes. For example, if we look at the ST graph, actually, let's look at the VT graph. So for the VT graph, if we draw, like, for example, from here to here, like a straight line, let's say we call this point T. We call this point, let's say U, which is the initial velocity. This is the final velocity V. Sorry, actually, I'll redraw this diagram. So V, T, and this is V, this is U, this is time T. So basically what happens is if we find the area, then we draw something like this. So the rectangles, the yellow rectangles area is UT. And the triangle above is V. So as you can see, the area above is also T times V minus U times a half. And obviously you can see where it's going. If we expand the brackets, this is UT plus half UT plus, sorry, minus half UT plus half VT. So what you have is half U plus V T. And this is one of the Suvat equations, actually. And the other Suvat equation, it's really easy to see. So I'm assuming you guys know this equation, v equals to u plus at. It's quite intuitive. If you sub that in, you'll get a half at squared plus ut. And basically that's it. And v squared plus at squared, v squared equals to u squared minus, v squared equals to u squared plus 2as is basically when you solve the equation, you eliminate t, so you can solve for the equation. I'm not going to derive it here though. It's quite intuitive. And let's move on to some problem solving strategies. For example, I have this question here. It's a very standard speed time graph question. So basically, these guys are having like a skiing race, and this guy called Marillo, I don't know how to pronounce it. It's basically this guy who's skiing has like this speed versus time relationship. It says Marillo crossed the finishing line after a time of 40 seconds. How long was the race? So obviously we have speed versus time graph. So we know that the displacement, we're trying to find the displacement because it's saying, what is the distance? So what we want to do is we want to find the area up to 40 seconds. So if we draw like a line here, so we're trying to find the area here. And basically it's a trapezoid, so you can find the area easily. I'm not going to do it here. It also says Sam finished after a time of 50 seconds. What was his average speed in kilometers per hour for the race? Notice how he said speed here. Actually, the graph is not even a velocity time graph, it's a speed time graph. The reason for this is that you're probably trying to find the total distance of the race, and velocity and displacement are two precise. It's literally like the straight line distance between 2 points, and it's path independent. And obviously, they probably want it to be path dependent or something. Anyways, it's not really important. It says Sam finished after a time 50 seconds. So obviously, after finding the total distance, what you want to do is you divide the total distance by the total time. So you'll get the average speed. And obviously you have to convert the units because they're asking in kilometers per hour. A very simple problem to start. This problem is 1D kinematics. It's one of the problems. It's not from IB actually, and it's a good practice for your algebra skills. And it says given the initial velocity u and final velocity v, find the velocity when the object is at the midpoint of the initial position and final position. So basically, you have this guy. Let's say this guy's walking at first at u, and then this guy is finishing at v. And also, by the way, you assume it's uniform acceleration in this problem. So what it's asking you is, what is your velocity at the midpoint of your path? And I see a lot of people saying, oh, it must be the average of the two velocities, right? That's actually completely wrong because it's just, you're asking for the velocity at the midpoint of the displacement, not the midpoint of the two velocities. So it's actually not right. So obviously at this point, you have to understand something that the total distance you travel is actually the same, not the difference in velocity. So let's say we set this velocity as x. So we want to write a Suvat equation that relates the distance and the velocity x. So first thing comes to mind is that, oh, we don't know the time. So obviously when you have a question, it's always easier to list out the 5 variables S, U, V, A, T, and you want to see which ones you know, which one you don't know. So at this moment, we know the S is D, because we set it as D. We know the velocity U. We know the velocity V. We do not know what the acceleration is. We do not know what T is. However, every single equation, I'm pretty sure, has to involve 4 variables. So what happens here is that we can set the acceleration as some A value, because we know it's uniform acceleration. So basically, we can write an equation that does not involve t, and there's only one equation that does that, which is v squared equals to u squared plus 2as. And at this point, what you want to do is you actually do this equation twice for 2 scenarios. The first scenario is for the first part of the path. The second scenario is for the second part of the path. So what happens is you list out these scenarios. And then you solve for x, basically. Because what we really have here is that v, actually we have 3 variables that are unknown. So we have x, a, and d that are unknown. So you can list out a third equation, which is, let me think. Actually, we only have 2 variables that are known here, because a is actually, it's just given, because we have to express the answer in terms of a as well. So you can solve these 2 equations, solve for x and d, and I think that's it. That's it for this problem. Interesting problem. And the second part is projectile motion. Projectile motion is basically 2D motion, and to be honest, 2D motion is not that different from 1D motion. You basically split the x and y component, and the key assumption for projectile motion is that x and y components do not affect each other, and they're completely independent of each other. So for example, if you throw a ball on Earth, there's a downward acceleration towards the Earth because of gravity, but that downward the downward acceleration force does not affect the horizontal displacement or the horizontal velocity of the ball at all. So that's a key assumption in projectile motion. And so we can generalize some projectile motion equations. So if we have like a ball, for example, throwing at this angle, what you always want to do is you want to list out that's how I always solve problems. So you list out the x components, you list out the y components. So SUVAT, SUVAT. And if we're talking about throwing this ball on Earth, we know that there will be no horizontal acceleration. So we know it's 0, and then we can list out, so u is u, v is also u because there's no acceleration. Time is just t, and then s is whatever you want it to be, and in this case it should be ut. And y component, we don't know, the s we don't know, u we know it's just u. Actually, let me just correct this for a little bit. And u is just, u cosine theta. Yeah, sorry, I messed up. So basically, you split the components. You have to be very careful. x component, u is just u cosine theta, s is u cosine theta t, v is u cosine theta, a is 0, t is just t. U is u sine theta. A is, in most cases, negative g because it's downward acceleration, but it really depends on the scenario. S is, we'll talk about that later. A is, yeah, we talked about A. T is always, these two are always the same because time is scalar, and the time for the ball is always the same, regardless of what component we're talking about. And V is u sine theta minus gt. And S, you can just list out some equations. And by this method, you probably can always find stuff like, you can see which variable you don't have. And by seeing these variables that you don't have, you can find out the quickest way. You can think of an equation that includes all the variable that you know, and also include the variable that you want to find, but does not include the variable that you don't have information for. So that's it. That's it for projectile motion, basically, because there's really not much to talk about for projectile motion. However, there's a lot to talk about for force and conservation of energy, conservation of momentum and stuff. So I'll see you in the next video.